Jorge, are you by any chance on a vertical monitor or
Yes, I am. Let me just swap again.
the aspect ratio kind of that looks better. I don't know what you did, but right now it looks full screen for me.
Okay. Let me just do it again. I was trying something, but just to how about now?
Yeah, that looks pretty good.
Okay.
All right, so we're already live and recording. So, welcome everyone to January 26th EPSP Connects. Thank you to everyone who volunteers with AGU's EPSP to help identify speakers, make sure that we've got everything ready to run our session every month, advertising and social media, etc. It's very helpful. It is my pleasure today to present Dr. San Juan. Dr. San Juan did his PhD at the University of Illinois at Urbana-Champaign and has been working on very interesting problems involving eco morphology, I guess, bringing those together with very, very fancy experimental techniques. Dr. San Juan joined NC State University, I want to say 2 years ago now. You'll correct me.
Yeah, 2.5. Yeah.
Okay, two
Mhm.
and a half years ago. He's an assistant professor there. And I'm looking forward to your presentation today. So please take it away.
Thank you. Thank you. Appreciate it. It's a pleasure to be presenting today in this EPSP um, Connect. Once again, my name is Jorge San Juan. I'm assistant professor in North Carolina State University. I'm part of the civil construction and environmental engineering, but more specifically, I'm part of the coastal engineering program. Um, so I'm part of that team. So the topic today is related to some coastal issues, coastal situations. So the title of my presentation today is Fluid Sediment and Sediment Flux in Low-Height Oyster Reefs. This is a experiment, a flume study on how oysters alter their habitats. So, but before I start, I would like to acknowledge that the work that I will be presenting today is the result of the support from many people. The people you see here in the screen these are my students: Javier Zumbado Gonzalez, a PhD student of mine; Juan Conde recently finished his master with me; and Nicole Barad, an undergrad student that's so energetic, and she's been helping us with volunteering her time. And also, I would like to acknowledge the support of North Carolina Coastal Federation, a nonprofit here in North Carolina that's been helping us to work through questions and helping us to figure out how oysters work in nature. And the work that I will be presenting today, it's framed through the research that my PhD student Javier Zumbado is conducting right now. So first of all, oyster reefs. Oyster reefs are very complex ecosystems. You say that they are they are habitats in coastal areas that provide a lot of ecological services. Some of these services range from water filtration, improving water quality, as they are filter eaters. They remove nutrients, they remove turbidity from the water column, but at the same time, they provide a structure, a habitat for invertebrates and small fish. So in that way, these small habitats also help to improve the fish production, so helping in a way or another also the economy of coastal communities, particularly in the East Coast. Here in North Carolina, oyster reef, they're also being implemented in nature-based solutions called living shorelines, which are these structures that are implement and living animals and living vegetation to protect the coast against erosion. So they are very good at attenuating waves. So they work as these barriers to minimize energy going into coastline that have been implemented in public land and also in private land. But the thing with these habitats is that in recent years they have been their their populations has been decreasing substantially. It's been estimated that around 85% worldwide it's been lost in these habitats, and the reasons are very broad in terms of the causes of this loss. It goes from over harvesting to low water quality, to impacts also in their habitats. So because of their ecosystem, the ecological services they provide, here particularly in North Carolina, oyster reefs, people wants to restore these habitats. Also, people want to find ways to conserve these habitats. So because of that, that's kind of like a motivation that we have to pursue, and ways to understand how these habitats interact with their flow, and also how they interact with the sediments. Improving their spaces, improving their ecosystems, depending on how well they can be placed. So, say for example, sediment transport don't bury them, or flow conditions are they appropriate for them to grow and propagate. Particularly the oyster reef that we're interested in this study are the eastern oysters. These are mollusks that they belong to the class Bivalvia. This type of mollusk has a particular shape that is compound of two shells. One is a flat shell, and the other one is a cup shell. So what you're gonna see in this study, some of the results that we have here in the model that we built, is that we're gonna have these replicate of this mimic of this geometry. We're gonna have a cup side, and we're gonna have a filled cup that is kind of like completing the flat shell that you'll see in a natural oyster. In terms of how they grow, they typically attach to substrate, to hard substrate. This hard substrate could be initially could be hard soil that can be found near the intertidal zone, but also they attach to each other. So this reef grows by attaching on top of each other. So the way how they need to through hard substrate. So we're gonna do is in this studies to show you the upper part of this oyster reef that we're gonna call low height or low reliefs, because we're only aiming to understand the behavior or the hydrodynamic and sediment behavior when we have only one layer of oysters. So our setup is going to look something like this. We're going to have oyster going to be attached to aluminum rod, and this aluminum rod is going to be placed in the flume. This, in general terms, these structures are three-dimensional. They're very complex. So their impact on the flow and the resistance that they're imposed to the flow is going to be very variable. If you look into the multiple scales that these oysters can organize themselves, we can see it through the three different sizes that we can see this structure. We can look into the oyster scale, like the single element, the single individual affecting as uniformly distributed patch affecting the flow conditions, or we can see them as clustered. I mentioned earlier that they grow attaching to each other. As they mature, as the oyster reefs mature, they start to clump into clusters. So you can imagine, and also the type of resistance that they impose into the flow is going to be different. Or we can find these very large structures that connect in long ridges that form these structures that are more related to bed form. The bed form scale, like large, like if you can think of an analogy to large dunes. So these are at least three scales that we can conceptualize these oyster reefs, and we're gonna explore at least one of these. I'm gonna have a little bit of a overview or what are going to be the next steps in terms of the closer part. So that's our study situation. Looking into the literature, some of the field studies have been compiling to what is their density, the number of oysters per unit area, the typical velocity that you can find in intertidal oyster reefs, and when we have tidal currents. And just to have a little bit of a reference here, our study is the one that is at the bottom, just to show some of the numbers. The water depth that these habitats can be encountered ranges from 1.5 meters to 20 centimeters. The setup that we have today is going to be 40 centimeters. The height of the reef for a low relief or low height oysters are going to be between centimeters, and the actual velocity of the flow is going to be between 10 centimeters to 30 centimeters per second. In our case, we have a rough depth average velocity of 22 centimeters per second. And just using this depth average velocity to try to estimate what friction coefficient you can get out of that, we have roughly a 0.02223 friction coefficient for the study that we have here. A little bit of a context of where our study situates in the larger body of literature. This literature review that is cited here, WU 2024, find out that most of the recent studies have been related to field test and numerical work with a few laboratory experiments. But one of the things that they have also pointed out in this literature review, this synthesis of literature, is that most of them are related to wave attenuation. Of course, there is a huge motivation to look into wave attenuation, because these oysters, they work as rigid structure, natural rigid structure that are just perfect for nature-based solutions. So they have been implemented as barriers to prevent, like living shorelines, to prevent erosion, shore erosion. So there is this need to look into how unidirectional flow, how a current is interacted with these flows when we have intertidal oyster reefs that are in the path of tidal currents. There is this study, LEAD 2025, that looked into a way to characterize the velocity profile when you have unidirectional flows in oyster reefs. They run tests in the flume as well. They have small scale models of oysters, and what they presented at the end of their study is how well a logarithmic velocity profile would fit when we have oyster reefs in a flume, when we have in an open channel flow and we have oyster reef. They come up with this expression with a macro scale Nicorazze coefficient. But one of the things that I also found is that the approximation to a logarithmic velocity profile is limited by the submerged ratio. And this submerged ratio becomes important because if we're dealing with intertidal oyster reef, like the one that we're targeting in this study, this range of submergence ratio, talking about submergence ratio, the depth of water to the height of the oyster reefs, varies along the tidal cycle. For subtidal oyster reefs, this submergence ratio is larger, so a logarithmic profile might be more suitable. The rate of the submergence ratio that they have in this study that started to break that logarithmic approximation was around 6.7. We are targeting here in this study a submergence ratio of 5. So we're within that range where we know that the logarithmic profile does not hold, and the results are going to show that. And lastly, if we want to look into putting the context how sediments have been approached in canopy flows or flow through vegetation at this point, I could point out to this study, San Antinoco 2021. They did this investigation to how well Rouse concentration distribution could fit within flow that is going through an emergent rigid vegetation. In this approach, they estimated an effective shear velocity that we're gonna fit into a Raussian concentration distribution. In this particular study, they implemented turbulent kinetic energy based shear velocity as a way to parameterize this shear velocity as a function of turbulent kinetic energy based on some understanding that the transport, or at least the pickup function that is going to bring these sediments into suspension, are more related to the turbulent kinetic energy rather than the bed shear stress that is happening that we know up to this point for open channel flows. So the questions, based on this, the question that we want to approach in this study is, can we predict the velocity profile and suspend the sediment concentration following a simple mixing length approach in low relief oysters? So a mixing length approach is this Prandtl mixing length theory that tells us that we can represent the shear stress as small eddies that are turning parcels of fluids, and the size of these eddies are going to be characterized by a mixing length. It's a very simple yet very powerful a theory that can actually give us the solution for the logarithmic profile. So our question is, can we, given this theoretical framework, apply it to get a prediction for velocity profile in a flow that is not necessarily logarithmic? And also, given that the mixing length is also the base for the Rouse distribution of concentration, can be extended into that estimation of a concentration. So what we did is that we went to the lab, and I say we as a royal we, because I did not go there. So what you see in this video is my PhD student, Javier, and he's preparing the oyster reefs, the oysters, and setting up in the flume and taking measurements here in this in the flume. So if I do if my job is done right in this seminar, I want you to, at the end of this seminar, to go with the idea that yes, we can use a mixing length when we do a flow characterization, that we can use a mixing length approach to at least predict some part of the velocity profile, yet we might be limited into the prediction of the spatial variability, because bear in mind that we have oyster reef. We have a spatial variability here we have a spatial variability in where they are placed, and also the resistance that is imposed into the flow. But we still can use that mixing length approach to develop the profile. For the suspended sediment flux, we might still use it, but we are still limited by that specific spatial variability. We're going to see later that spatial variability introduces a change in the mode of sediment transport within the reef when we have sparse, when we have dense, tightly packed oysters, and that type of scenarios cannot be captured with this mixing length approach. And at the end, I will show a little bit of what would be the next steps for us in order to get model parametrization here. So let's start with the flow characterization. So as I said, we went to the flume, where we went with the real we again. And in this flume, we could get velocity here up to 1 meter per second, down to 0.1 meters per second, 10 centimeters per second. But for this experiment, we stick to a single flow conditions and to density of the oysters. We took velocity profiles with an ADB, a Vectrino profiler, and we set up oyster beds. These oyster beds look like this. Each individual oyster is a real shell that we collected from the North Carolina Coastal Federation shell recycling program. Javier collected this. He washed them. He filled them with an epoxy, and he put an aluminum rod right at the center, so he could have these models for oysters, and he could place them around 1,000 of these oysters. He prepared them this way. The oyster can be placed in a random distribution in the flume, and also he can randomly set the orientation around the axis of the aluminum rod. For the velocity profiles were taken for two conditions. The first conditions were the sparse case, when we have 100 oysters per square meter, and when we have a dense condition with 400, for roughly as twice as we have for the sparse condition. So Javier did 3D model, a DM of these arrangements using structure from motion, which was very convenient because after doing this structure from motion, he could process the DEMs to get the distribution of the porosity. So remember here that we want to know what is the resistance that the flow is imposing into the flow, what the oysters are imposing into the flow, so we can have the tools to predict how the velocity profile is looking. So based on these DEMs that were taken using structure from motion, Javier then reproduced these profiles of porosity. So these are average porosity that also can be related to volumetric frontal area, because it's going to be part also later on the momentum equation. But at this point, what you see here is how these two porosities, how the two profiles are changing. Of course, when we have sparse conditions, we have less porosity. When we have dense conditions, we have more porosity here. And also we took 4 velocity profiles, 4 positions in both, to understand also what is this variation in space. Once again, we have a 3-dimensional structure here. There's going to be, and also randomly distributed, we're going to have here a velocity distribution that are different in different locations. So in 4 different locations, Javier took different velocity profiles, and he had 3 replicates. So he set up 3 different distribution for dense, 3 different distributions for the sparse condition to improve the statistics of the result that he was getting. So a little bit of a mixing length theory here. For the mixing length, we started with the Navier-Stokes equations, and we did a double averaging of these Navier-Stokes equations. So we did with a double averaging of the momentum equation. The first thing that we did was the time average. This is the most common equation that we know of the Navier-Stokes, the RAMS. We time averaged the Navier-Stokes equation over the turbulence. So what I mean by that is when we took our velocity measurements at a single point, that velocity measurement gave us a time series, and our time series was decomposed according to Reynolds, the Reynolds decomposition. An instantaneous velocity is decomposed into a time average velocity plus deviation from that time average velocity, which is our turbulent fluctuations. So that was the first decomposition that we did to our velocity measurements. Now, the second averaging that we did here was a spatial averaging. If you remember, we have the 4 different profiles that we measure, so we could have that second averaging of the velocities. So in this case, we have a single point that is our time average value that is decomposed into a spatial average component plus a deviation from that average. So it's a very similar, it was a very similar concept. So what we did with this is that now we have this decomposition, and when we focus specifically on the streamwise direction of the momentum in the streamwise direction. And this, what I'm going to show here are just the components of this equation. We're going to have first the pressure gradient as part of this momentum equation, we have then the Reynolds stress contributing to momentum, and then we have this term that typically comes from canopy flow. It's called a dispersive stress. And this dispersive stress is kind of an equivalent to the Reynolds stress that you might be familiar. But in this case, it just takes into account that covariance between the time average of the velocity. So it's an equivalent to the Reynolds stress, but in space. You could think of this term that way. It's called dispersive stress. And finally, we have the canopy drag. If we have vegetation, if we have obstacles in our flow, we're going to have some drag there. So if we have an equation that needs to be balanced, needs to be conserved, everything needs to be equal to 0. So our velocity profile is going to have a different simplification based on the different areas where we're at. A typical velocity profile for a canopy flow is going to look like this. We're going to have a velocity that is faster at the top, that is slower within the canopy. In this case, it's oyster, but it could be vegetation. We're going to have an area where we have a free stream. An area where we have a free stream. In this free stream, there is a minimal effect from the bottom. Then we're going to have an area where the velocity profile starts to feel the drag from the canopy, and we're going to call this the form-induced layer. And then we're going to have this other section right below the canopy top. And in this section, we're going to call it the canopy layer. And finally, at the bottom, we're going to have the near bed layer. One thing that I want to point out is like the canopy drag is only going to be present in these two, the canopy and the near bed, the canopy layer and the near bed. Now, the Reynolds stress, term is going to be present in these two. So it's going to be important because we're going to have two approximations for that. The first approximation is the pressure term. The pressure term is going to be approximated by the maximum Reynolds stress or the shear velocity. And the second approximation that we're going to use is right here, is the mixing length approximation. That you see at the bottom, that's the mixing length approximation. And what is really important about this one is that you take here into account the velocity gradient. That's an important term here because that's when the term that is easy to measure is a term that is going to give us an estimation for the Reynolds stress, which is part of this momentum equation. So how does it look like? So what you see here are the results of the velocity profiles. These are measured velocity profiles. Orange is going to be the sparse conditions, and blue is going to be the dense condition. They look they look very similar, but the main difference that you can see is at the very bottom. The very bottom is when you see more of a difference between these two velocity profiles. These are the velocity profiles, but we looked into the actual velocity gradient. I mentioned this is important because it's going to give us the indication of how this mixing length is going to play out in our velocity profile. One thing that you can notice in this area is that it's larger between 0.4 and 2.5. And in this region corresponds to the region where the shear stress, where the Reynolds stress are important. It is important for the mixing length is because the velocity gradient is part of this mixing length approximation. So we know that we're going to focus in our velocity profile in that range because above 2.5, this is normalized elevation. Above 2.5 is almost 0, and very close to the bed is almost 0. So this is going to be our mixing zone. We're going to focus on that part and see if we can predict a velocity profile from that. The second thing we're going to look into it is how the Reynolds stresses are changing. Reynolds stresses is an indication of the intensity of the turbulence. It's not necessarily a turbulent kinetic energy, but it contributes in a way or another to the turbulent intensity. But what we have here is the Reynolds stress. Reynolds stress for canopy flow is a time average approach. Reynolds stress is a time average approach. The two are normalized by the shear velocity, and they look very similar. But when we looked into the dispersive stress, remember, the dispersive stress is kind of like the intensity of the variation in space. There is an important difference between the the dispersive stresses when we have sparse conditions and when we have dense conditions. The dense conditions are tightly packed. The variation in the velocities in the space between oysters are going to be reduced if we compare it against the sparse conditions. The sparse conditions are going to have and going to allow more space and going to allow more variability in the velocity profiles. As a consequence, our dispersive terms are going to be more important, to the point that they are not necessarily the same magnitude that you would expect for the Reynolds stresses, but they are comparable for the sparse conditions. So where do they participate? They participate in that part where in the canopy region, right below the top of the canopy, in that part where the Reynolds stress and the dispersive stress are competing in the momentum. That's the part where it's going to be important, and we're going to see that when we looked into this balance of the momentum. The second thing, the next thing that I want to show you is how the actual turbulence is working here. If you remember in the introduction, I showed you this study from Sen and Tinoco 2021 that is looking into a turbulence-based approach for sediment transport. Because turbulence within canopy flows are higher, they're going to have a more important role into picking up particles by pressure difference and intensity of turbulence near the bed. So one thing that we looked into here in the left plot, you're going to see the turbulent kinetic energy for the two conditions. This turbulent kinetic energy, once again, is a time average approach. But for the plot on the right, you're going to have this turbulent kinetic energy that has that is taken into account the intensity of the spatial variation. One thing that we notice later on the sediments is that in the sediment transport is that this spatial variation plays an important role into how sediments are moving. You're going to see it later in the second part of this talk. But here, what you see, it's how turbulent it is in between the oysters, and later we'll see that in the result that is actually important to take into account the space availability in between these oysters. So when we looked into the actual momentum balance here, we're gonna have that the equation at the end of the day becomes equal to 0. One thing that I want to point out here is that we don't necessarily have at this point an actual way to model the drag force. So the drag force in our equation becomes that free variable, like calibration variable, you may say, that is going to help us balance these momentum equations. And that drag force is going to be important, of course, where the oysters are. And these oysters are below that line that is number 1, which is when the elevation is normalized by the height of the oysters. There is where the drag is becoming important. And also that is the place where the Reynolds stress and the dispersive stress start to compete with each other. What I want you to pay attention here is how the dark points, which are the dispersive stresses, start to fluctuate of the side that you can see them when they are participating in this momentum equation. You have the flow velocities on the very right, just as a reference to where you're at in this velocity profile, but the dispersive stresses becomes more relevant within the canopy, of course, for the sparse condition, affecting also how this how the drag term is going to behave. Looking into the drag term, I'm going to show you here how the actual drag coefficient looks like as a way to as a parameter that we use for calibration. I mean, what I mean by that is like that parameter that we are using to close and balance the equation. The range of drag coefficients, they vary a lot because we could solve for this momentum equation in different locations in space. We pretty much have a localized drag coefficient to solve for this equation. But at the same time, when you see approximations to the drag coefficient equal to 1, equal to 1.5, or sometimes equal to 2. The result that we're getting at the localized space, they tell us a slightly different story. One thing I also want to point out here is, like, for us to come up with this drag coefficient, we need to we find out, of course, that this drag coefficient is very sensitive to the actual velocity magnitude. So you have here in this term a velocity that is squared. And if you solve for this drag coefficient, you're going to have this velocity squared divided on the other side of the equation. So what is happening is, like, where the oysters are the place where the velocity is the lowest. That small velocity to the square in the lower part of the fraction is going to give you a very large number sometimes. So depending of how small the velocity is, this drag coefficient becomes very sensitive to that value of the velocity. So now we have that a drag coefficient. Now we have a momentum balance for that, for the whole velocity profile. So now the question is, like, can we use it to predict the velocity? So what you see here in this plot is a mixing length that is computed from the Reynolds stresses. And when we use that mixing length computed from the Reynolds stresses according to the approximation of the mixing length, we can find this expression. In this case, we have a parameter alpha that could be, for this case, 0.13. And using that information, we can predict, or we can at least adjust our data. We can adjust a model to our data, but of course, is using the data itself to fit it. What would be important here for next step would be to implement, to see if this model applies to other conditions. But in this case, what we have a mixing length model that is working in an area of the velocity profile that is affected by the oysters, that is creating this inflection point, and that is not necessarily logarithmic. So in this case, we're still implementing a mixing length approach that can give us a solution for a velocity profile. So at the end, we can think of this part that the oyster reef, they create a strong shear zone and can be represented with this mixing length. But the spatial variability, given the boundary condition of the canopy top, but the spatial variability is not necessarily captured through this model. So looking into the suspended sediment flux, the only difference that we did in this time was just to fill it with sand. Here was sand of around 150 microns. We took suspended sediment measurements as a proxy with turbidity sensor and an ADV. And then we also have a water sampler. We had some issue with the water sample later, but we're going to see some approximation of the suspended sediment transport. For the suspended sediment transport, if you remember conservation of mass of suspended sediment, we're going to have a mean flux of suspended sediment, and that can be divided into parts. One is the convective, the velocity is moving the sediment, and the other part is the Reynolds flux, where the turbulence is actually making the sediments to go away, to move. So the approximation is that this Reynolds flux can be approximated by a Fickian law through a sediment diffusivity. But well, a sediment diffusivity could be later approximated to an eddy diffusivity sometimes, but not quite. The fact that we have a particle that has some mass, they not necessarily follow necessarily the flow, the eddy that is moving this particle, and the same way as the momentum is being moved through this eddy viscosity. So we have to take that eddy diffusivity equal to the sediment diffusivity carefully. But when we have equilibrium condition, is a very convenient way to apply this to have a solution for the sediment concentration profile. if we happen to have an expression that tells us what the mixing length is, can we apply an expression for the mixing length to solve for the concentration profile? That's the question that we want to explore. So what we're gonna see here in this slide are the results for the velocity measurements now when we have sediments. The velocity measurement and also compared with the bare bed. They look very similar in general terms, very similar. We have in sparse condition, faster velocities at the bottom and slower velocity with the denser. If we looked into the Reynolds stresses and the turbulent kinetic energy, they, in general terms, they behave very similarly. One thing that I want to point out is that for the sparse condition, the turbulent kinetic energy tends to be a little bit rounded in this case. Remember, for the sparse condition, we have more space in between. The output of this, the outcome of these processes is that we're going to have for the dense case very reduced development of bed forms in between, but for the sparse condition, because we have more space, because we have more variability of velocity in between, we're going to allow more sediments to move and we're going to start to develop more bed forms. And that's one key difference between the sediment transfer behavior between these two different conditions. We have development of bed forms in sparse conditions because we're allowing more space and we're allowing more variability. Looking into the turbidity as a proxy for suspended sediment at this point, we're working on the calibration right now. I want you to focus on the left graph. You'll see that the dense condition has higher turbidity above the level number 1, which is the level of the top of the oysters. That part, based on observations, seems to be related to the fact that a more constrained space in between forces the sediment to be shoot above the oysters. Whereas when we have more space in between the oysters, the sediments are more freely moving in between the oysters. And that's one thing that we can notice on the right side, on the plot on the right. What you see here is accumulated suspended sediment load. Once again, here is as a proxy using turbidity. In general terms, we have more transport of sediment through the canopy, through the oysters than for the sparse condition that you have it for the dense conditions. And the association that we're thinking here is related to the fact that we're allowing more sediments and more bed load to move sediments in the lower part of the velocity of the profile than in the upper part of the concentration profile. So if we use this mixing length approximation and we solve for a theoretical sediment concentration, we can compare on the left the actual turbidity that was measured, on the right, and on the right you're going to have the theoretical concentration if you were to use the mixing length. The first difference that we can notice between these two plots is that the theoretical mixing length approach for the sediment concentration is telling you that we're going to have more concentration of sediment for the sparse condition in the water column, which is not the case that we observe in the data that we collected for the turbidity. Once again, here this mixing length approach works well for the velocity distribution, but it's not necessarily capturing the space and the variability that you can find in between the elements in the reef. So the reef induces a shear zone to interact with the flow with the spatial variability of the flow. And the mixing length can actually represent the velocity well, but when it comes down to be used directly to predict what potentially the sediment concentration profile would be, it falls short because it's not capturing necessarily that spatial variability that you can have when you have more sparse distributed elements. So in this very last step, this very last part, I want to just give you an overview of where this research is going. One thing that we did is we went to the field and we wanted to bring some of the more natural distribution, because now at this point we're learning that the spatial distribution matters. We wanted to bring more of the natural distribution in order for us to have a more realistic parameterization of these habitats in ecomorphodynamic models. So we went and we took pictures to recreate DEMs of this through instruction from motion, and we recreated these patches of oysters. We identified some of the clusters that were then 3D printed. Now the idea is to bring these natural structure, 3D printed natural structures of oysters into the flume, and also identify a parameter that can give us a quantification of the spatial distribution. With that spatial distribution, we want to understand how the morphology of the bed is being developed under different spatial distributions. And for that, our idea is to implement the bed form analysis method for bathymetric information from Cisneros 2020, Bambi. This algorithm may help us to have a statistical distribution of the geometry as a way also for us to have a better understanding of how resistance is being distributed through a patch of oyster reefs. Finally, we like to find ways, strategies to implement that and to bring it into a larger scale ecomorphodynamic model, where we can have modules for oysters that can interact with the sediment transport equations, but at the same time can help us see how the bed is evolving also in time. So our aim at the end is to develop this hydrosediment framework for oyster reef that could be implemented in models that can capture the flow resistance as it's been distributed in space, but at the same time, the sediment transport processes changing in space. For that, I'm going to just keep these conclusions up, and I'll be more than happy to take any questions.
Thanks, Jorge. So there is already a question in the chat. It came in early, so I don't know if it might have been, I don't think you addressed it anyway, but the question came in at around slide 12 or so, but is skin friction the most relevant roughness measure? What about form friction? In parentheses, thinking that oyster bed's 3D shape might conform a quite substantial form drag shape.
Absolutely. Yes. Absolutely. 100%. Right now, the approach in that estimation that was presented, you might have seen that we have this depth average velocity. The fact that we're taking the depth average velocity to have an estimation, the depth average velocity that is measured, that it already takes into account the velocity profile that was created by the oyster. And based on that velocity distribution, we got a friction coefficient. One way or another is already taking both into account. One thing that comes into my mind when in the discussion with Javier, when we're discussing about the friction, is the Einstein approach to resistant partition. We may know that we're going to have this bed form partition between the bed forms and the skin friction, and then we have the summation of those two. Up to this point, the idea is to think of friction in a similar way, to think of a friction that can come from form-induced friction from the oysters, form-induced friction from the bed form development, given that sometimes it can be developed on bed forms, and then a friction coefficient that comes from the fact that we have a roughness from the grain. But that was a good question.
All right, and a bit of a follow-up with the bed forms. This is for me. Those environments, in my mind, they're quite muddy.
Mm-hmm.
but you're still, modeling with sand. It's not easy to put mud in your lab. I get that. But
Yes, yes,
if
exactly. Yeah.
how much sand do you actually like? What might be the percentage, at least, of the environment that you're trying to mimic? How much sand do you find out there, and how likely is for bed forms to actually show up?
Yeah, well, actually, the these habitats, they grow in both. Actually, most of them are more muddy. The picture that you saw, they're extremely muddy. But we have some sites here in North Carolina by the Rachel Carson Reserve that we've been visiting. We're gonna visit them during the spring too. That they are actually growing around salt marshes that are next to they're next to sandy beach. They're next to sandy beach. There is some growth of organic matter. There is some level of fine material that is there. But they are, I'm gonna say that they are in my majority, they are more granular than fine, but we're gonna have this mixture of the two of them. At this point, that's a good point that you're bringing in terms of the development of the bed forms, because the bed forms are going to be developed in this case based on the granular behavior of the material that we have. Um, and we are looking right now into the actual transport in the bed form that is developed, but we acknowledge that there is that part of the mud part of the muddy of this fine sediment that we're not necessarily capturing here. It's still kind of like in debate if we're gonna do it or not. Um, but one thing in terms of the natural environment, they do grow also in sandy environments as well as in fine material. That's kind of like the point that I would like to to bring to.
And do they secrete or produce any kind of substance that
They
might
do.
bind sediment
They
together as
do,
well?
yes. They do have these, they call it pseudophyces. The pseudophyces, there's organic material that they also excrete, and they also have around. And actually, that's a good point that you're bringing it up, because in that illustration that I have earlier, that comes from a proposal that we're working on right now, that tries also to look into the modification of the substrates as it is around the area. There are two ways how these reefs modify the substrate. The first way is through the pseudophysis that makes, in a way or another, makes the material more cohesive. But the second way, how they also modify the substrate around them, by doing that, also affect how the sediments are being going to be moved after that. It's through shale hash. This shale hash is light material, but it's larger. So it is a very interesting transport transport set of property that this material will have, that will make it even more movable, but at the same time larger. So it's a very interesting way how they are also modifying the substrate, the sediments around them.
All right. Any more questions from the audience? Haven't seen anything come through. Oh, there's a follow-up there. So, what might be the relevance for oyster beds develop, for example, in channels or beaches? In my brief experience in tidal channels, depending on where they establish, the interactions between flow or bidirectional flow, oyster beds growth, and sediment dynamics make an interesting interplay. So basically, what's the role of where they actually grow, where they develop?
Is the question, if I understand the question correctly, is it related to the environmental conditions where they grow?
If they,
Is
yeah,
that?
depending on where they establish. And then Alejandro, if you want to unmute yourself, in case that you want to clarify aspects of the question, feel free to.
Mhm.
Sure. Thank you, Jorge. Very nice presentation. No, I was just curious about, I guess it can be both ways, right? So where these oyster beds develop, they of course modify the flow dynamics, and therefore there's an interplay between the bidirectional flow, well, in the case of tidal channels, of,
Mhm.
in the bidirectional flow, the sediment transport and the growth of the oyster bed itself. And depending on whether it's in some straight reach of the channel or a corner, a bend, all those interactions between those three factors, the oyster bed, the flow, and the sediment, can make it a quite interesting, complex thing, not easy to study in a in a
In,
flume.
yes, exactly. Yeah, I see your point. I see your point now. Yeah, absolutely. That's always the limitation of a flume experiment, of a flume study. It's isolate and focus on a specific process. In this case, well, I agree with you. I acknowledge what you're saying. There is so much complexity in where they grow, all the sediment dynamics, or actually the substrate and the sediment transport that goes around them, and the hydrodynamic conditions that surround them. And of course, in the field, in the flume, it's a little bit more way more trickier to try to reproduce those complexities. I think that's where the dual, like the dual collaboration with field work complementing, with the flume complementing the field work, or the field work complementing the flume. Actually, that two-way collaboration, that's where it becomes really relevant. One thing that I also want to point out here, I didn't present it in here. Javier has, as a third part of his PhD, after he finished with the sediment part, is going to move the setup that very similar to the one they have right now, sediments and realistic oysters into a oscillatory tunnel in this other facility that is new in our university, in our lab. He wants to focus more specifically into once again, isolating processes into the wave boundary layer interaction with this structure, and as a result, what type of sediment dynamics he will observe there. But yeah, kind of like to diversify a little bit more of or trying to bring more diversity into the complexity of these systems. But yeah, I agree with you with how complex they can be in the field.
All right, we're almost at the top of the hour, so I don't see any additional questions. So just thank you again, Jorge, for this excellent talk. For those of you still listening, next month we have two speakers. We're going to be having a conversation about wood in rivers. Dan Scott and I'm blanking out on his first name, Shobi. You'll find out. We'll send the flyer out with all the details soon. Thanks all for joining today, and we'll see you